So welcome everybody. Today we've got Ignacio from Barcelona, and he's I'm told he's now fully back in Barcelona, and he's going to tell us about activity-induced interactions and response in active matter.
Okay, thank you very much, Stani. Yeah, I mean, since some of you ask me from time to time, I was director of CCAM for 6 years until the end of 22. Then I was in Switzerland, but now I'm fully back in Universitat in Barcelona. So the title is relatively generic, and actually, I mean, I don't think I have to introduce too much what is active systems and why they are interesting and relevant. I wanted to, I mean, the fact that they are out of equilibrium imply that, does this work? Maybe it's, there's a bit of delay, yeah? I didn't check this before. Okay. Do you have this pointer? Doesn't seem to work very well. Maybe it will be better using. Yeah, no, this is my pointer, but is there no pointer? Yeah. Okay.
Yeah. So they have their own pointer.
And now it's there. Now it's no, but I see it here, but not there. So yeah, that's the point. That's because of the zoom. Okay. I can just. There is this pointer. Okay. I can use this pointer. Okay. Perfect. So one of the, I mean, there are a number of implications that these systems that are out of agreement have, and one of them is how they lead to new type of interactions and structures when you consider ensembles of these active particles, or for example, mixtures where you have active and passive particles, where passive particles, these are experiments and active particles that say move by diffusophoresis. In combination with silica particles, they can attract and form different type of clusters and gels due to their activity. And the mechanisms can be diffusophoresis, they can be diffuse osmosis. There are a number of physical ways in which then you can form or structure new patterns and new type of aggregates that will self-assemble. Or and you can use those to say, this is now an inclusion in an active pneumatic, where again will be moving, and you have other ones will also interact, and you can use them. This type of aggregates I was telling can also be used to manipulate and control. For example, this was a movie that is not working. Yeah, okay. In microfluidic channels, where they can use now these active self-diffusophoretic particles that are also sensitive to magnetic fields to aggregate them and move them along confined environments. Another aspect that is important of these active systems that I will also come back later is the fact that they are very dynamic. So they can form order structures, but also they are characterized by situations where there is a lot of disorder, and this is again the same active pneumatic I was showing before, and this type of disorder, chaotic motion, we know is not specific only of this system. It can be found in bacterial suspensions, in cell monolayers, and to some extent this has become like a model system to study the properties and the behavior of these chaotic or turbulent structures that they also form, not only ordered ones. So in this talk, I will actually tell 3 short stories. I thought it was good to give a number of stories since I will be around. Can be also a way to open further discussions. So I'll be talking in the context of these interactions about the nature of effective interactions, to try to understand better what they are in a model active system. And actually, this will lead me, as an aside, to see the impact that these effective interactions have not only in the interaction and the motion of inclusions, but how the inclusions can alter themselves, the nature of this bath. Normally, we think in these particles that we put and they react, but they can have a strong feedback into the ordered phases of an active bath as well. I will also mention one example. And in the third part, I will talk about this chaotic behavior in active pneumatics in 2 and 3D through some of the numerical studies that we have done. So I will start considering, I mean, we all know, I mean, it's good to have model systems for this inactive matter, and one of them is the active Brownian particles, where basically we have standard Brownian motion according to the net force acting on each particle, and the particles simply self-propel with a characteristic velocity along a director. If the director is in 2 dimensions, we parameterize through the angle, and the angle performs a random walk. That's basically all we need to go from the equilibrium system of colloids that we all know to now have a system of active colloids, and we know active particles that diffuse, and actually that leads to what we know as the motility-induced phase separation, due to the fact that when particles collide, these collisions will have a certain time and extension, because these particles are stubborn as they keep on colliding until they can rotate away. This model system is good because it tells us that essentially there are, if we disregard the translational diffusion, there are essentially 3 parameters, that characterize their behavior: the volume fraction or area fraction, the active Peclet number, which is a ratio between the time the particle takes to rotate with respect to the particle, the time it takes to propagate its own size, sigma is the particle size, and gamma here is like the ratio between the strength of the conservative forces and the strength of the active forces. I will take this very large, so particles will not really overlap, will not even to cross each other because of activity. So essentially, the phase diagram is characterized, it's a plane, so we have phi and the Peclet number, and we know that as we increase Peclet number, these are results for 2-dimensional disks, hard disks, I mean almost hard disks with very steep repulsive potential. We'll have MIPS, motility-induced phase separation, and we also know that if I now decrease Peclet towards 0, Peclet 0, now this is 2-dimensional hard disk where we have, this is an zoom or what's going on here. So we'll have the fluid exotic solid, and the fluid exotic is first order, and the exotic solid is second order. And then as you increase the activity, at some point this transition also becomes second order, and then but you still have this, the fluid exotic solid, which at some point will sort of like merge or cross the motility-induced phase separation, and this tells us that this motility-induced phase separation is a truly non-equilibrium phase transition that is kind of like independent of the extension of what would be the usual transition scenario that we have for equilibrium disks, now extended into the active phase. No. Yes.
So that doesn't really affect the results of the event.
I didn't say that. This is the results when D naught is 0. But indeed, D naught may have an effect. I mean, the outcome from here is that, I mean, what we know by changing D naught is that typically MIPS moves around, but doesn't typically lead to a qualitatively different scenario. So I would expect that the topology of this phase diagram, where you have the extension of what is the equilibrium phase transitions, and then MIPS will remain changing D0. But yeah, it's always a bit difficult to make no very strong statements. That would be my guess. Okay. Now, what we have done is to add to these interactions the possibility now of particles to tend to align, so that basically we can reproduce in active systems, even if we have disks, the analogous scenarios that we know for active particles that, because of their shape, they kind of have a tendency to form polar or nematic order. So essentially here you have the same equations I showed you before, where now we have introduced an aligning interaction if within a certain interaction range, and then this will tell us that if this constant k is large enough, we expect particles to, it's like Kuramoto type interaction, and then we know that the synchronization of these particles in the Kuramoto language leads to this polar order. And indeed, this is, now we have an extra parameter in our model system, because on top of the volume fraction or area fraction and the Peclet number, we have now a ratio between this constant k. Here I put kBt. It's basically because I was thinking that I scale d theta with kBt, but it's the ratio between these two scales that matters. And essentially that leads to Now we have another axis, which is area fraction. But if I look at a given area fraction where I can have a motility-induced phase separation, what this tells us is that increasing this alignment, so here we have the disordered phase, here is the MIPS phase, and then here we have two facts. As G becomes large enough, as alignment, when alignment dominates, there will be a transition to a polar ordered phase. And this is signaled by this discontinuous blue line here. That's the flocking, in a way, flocking transition. But then if we stay below that, then typically the alignment favors MIPS. So it's still disordered, but then again, qualitatively, you can imagine that as particles come together to form these MIPS clusters, the tendency that they have to be aligned will hinder the effective rotational diffusion that they need to escape, and therefore induce a MIPS phase more easily. But this is just to give the background of the model system. What I want to look at, as I said, is what happens now if I take this bath where we have active running particles that can align, and I introduce two inclusions. So this is, again, the sort of phase diagram that I will be using, essentially the equivalent to this previous one, but a bit more detailed in terms of what I'm going to show. I will stay below MIPS, so volume fractions are not that large. I don't care. So essentially, I will be comparing what happens if we are in the disordered phase here in white, or in the polar order phase when we have the flocking transition in this gray area here. Okay. And here I show you snapshots of how these active particles will look like. I will show you results in 6 selected points. 3 of them are at G0, so basically there is no alignment. This is active Brownian particles. And then what happens when the alignment brings them to the polar phase, and then I can compare them. And actually in the polar phase, I distinguish a case where, in this the polar phase has if you look at the order parameter, there is a non-zero alignment order parameter. But if you look now at the cluster size distribution, you can see that particles form clusters. The cluster size distribution sometimes in this region here, what I mark as red, for the system sizes that we could sample, are characterized by an algebraic decay, which is a power law. And essentially, this is kind of characterized by the fact that you have clusters that can become as large as system size. And that's not true in these other cases. So that's why we explore these points. And what we do is we put 2 particles. So here you have like two disks. These disks interact with the particles with potential that they have. And as a result, also it means that the active particles will not be able to enter the inclusion. The inclusions are always larger than the active particles. But when they collide, the alignment doesn't change. So it means that colliding particles will need a bit of time to move away. And you can see that naturally leads to an enhanced probability, typically, of the amount of active particles around the inclusion. Now, this is in the disorder, and these are in the polar phase. So you can see how particles move around the inclusions. As they move, typically, again, if you are in this region P2, where you have these large bands, they tend to be very much affected or correlated with the motion of the bands. Here in the disordered phase, you can see that they tend to, I didn't mention this, but the color here indicates the direction in which the active particles move. So the fact that here is blue means that there's really all of them are moving along the same direction. But here in this case, when the Pecla is not very large, they will have a tendency, you will see sometime later, to form, particles really cluster, and the alignment around the particle dominates their local arrangement.
So you look at the local exact.
No, what I will, this is just a movie. What I do now, I have these 2 particles, 2 inclusions. They move around, and then I can look at the probability distribution. Now I will focus on what is the arrangement of these particles to identify if they statistically attract or repel. Here we cannot talk of potential, but I can compute also the force. So I can also see how they distribute and what is the force between. That's basically what I show you here. So you see the movie, so it's kind of like very diverse. But if I look at the probability of having the 2 disks at a given distance, Now here is again for these 6 points, and then the blue squares is the equilibrium case. So because we have particles, I mean, it's repulsive, very short range. So, and then we have disks that are larger than the active particles. Then the blue squares is just the usual, I mean, this probability distribution corresponds to a depletion interaction, effectively. And actually, when we are in this point, so when the activity is weak, essentially, this is the blue curve, we recover a behavior that is the equilibrium-like depletion. This depletion now changes as we move, if we move up in this disordered phase. So it's a bit busy, but if you look at the green and the purple curve, so the green curve and the purple, so the green becomes quite repulsive. So this, I mean, probability of finding two particles becomes much smaller compared to the equilibrium one. So this is an effective depletion repulsion. And then this depletion becomes less, weakens as we increase further the Peclet number. So the behavior is non-monotonous when we move up. And when we are now in the polar phase, again, in this point here, the interaction is strongly repulsive. And while in this P2 and P3, which are now the red and this orange, again, they become essentially quite attractive. So as we move in this phase diagram, we go from attraction to repulsion, weak attraction again, strong repulsion and attraction, okay? Effectively, in terms of the P of D. We can also compute the force. I mean, actually, this strong repulsion, it was maybe not clear in the movie, in the previous slide, but typically what we see here is that there is, I mean, the Peclet is weak, but there is a strong tendency to align. So basically, particles, when collide and tend to stay around the obstacle, they form essentially the inclusion acts as a nucleation site for what is essentially an aster, and then two of these asters, which can be quite large, will repel each other. Okay. While in this case here, the formation of these bands that move around very dynamically, sort of like tends to sweep particles along, which effectively leads to an attraction. Now we can compute the force, and again, maybe we can start here. So A1 is the equilibrium force, and P1 is the force here that is repulsive. So you can see that indeed, I mean, there is the magnitude can change quite significantly. Also, the decay is much weaker, much slower when we have activity. And if you look now at the other cases here, also if you compare forces, I mean, this is sort of like compared to 1, which would be the equilibrium magnitude of the magnitude of the equilibrium force. You have here factor 2 or factor 5 or 10 maximum. And what we also found that I was not expecting, and I didn't have a strong feeling about it, is that if you take now this probability, you can also compute the ratio between, I mean, you can take the log of the derivative of the log of the probability, and in equilibrium, that would be like the effective force between them, which here doesn't need to hold. But I mean, in this case, what we see is that computing the force through the probability, which are the dashed lines, and comparing with the points, which are the force measurements, they are not very far. Okay, I don't see a fundamental reason why it has to work, but it's a fact that we see in this case. Well, I mean, I don't know if you want to go that direction. Yeah, yeah. I don't know how deep this is. Yeah, but. The scale is different, but they still follow each other. So yeah. Now in equilibrium, also what you can do is you can measure. I mean, here getting statistics takes time. So in order to improve the statistics, we thought in doing what you do in equilibrium, which is rather than following the two disks as they move around, is to fix them at a given distance and gather statistics. And what we found is that the behavior is very different. So again, here that doesn't work. So this is again a movie of the 3 where now disks are fixed. And essentially what happens qualitatively here, because is that the disks act as nucleation points for the organization of the active particles around. And because they are not able to move around, in this case, there is the separation of scales that basically generates a different type of interaction. here you can see more clearly what I refer to as the tendency to form these strong, sort of like polarized disks around the inclusion. So if you measure the forces here it's only the force that you can measure. I mean, the force is typically, I mean, again, this is the equilibrium case. In equilibrium, I mean, this is for the A1. When we are close to equilibrium, essentially, the forces that we measure agree. But then for the other cases, forces are typically repulsive and much larger than the ones that we measure when the disks move around. So that's also important in the sense that there is a difference in the measurements between mobile and fixed inclusion. So interactions here depend on time scales. And you can try to rationalize that by thinking that now you have two time scales. You have the time scale in which an inclusion would move around, diffuse around, but you can sort of like compute from a decorrelation for the time of their displacements, and the decorrelation time of the polar order, how the active Brownian particles, which tend to organize around, will lose their correlation that is characterized by their orientation. And here then you can understand that in the disordered phase, if the Peckley is small, the time scale in which the active particles relax is faster than the scale in which the inclusions diffuse, because they are larger, and therefore this is like more like the equilibrium, like a scenario. But then as you increase the Peckley number, basically particles start moving around on time scales in which the active particles around them have not the time to really relax, and then it creates effectively like an effective particle that consists of the disks and a set of active particles around them. And that sort of like could explain why in the disordered phase we have this reentrant, or this change in behavior between attraction, repulsion, and attraction. We started looking at what happens when you have many particles. So these are not really large systems, but then what we learn for two particles, can we then use it to understand how now a number of these disks will move around? And actually, again, I mean, when we are in the regions of large clusters of aligned particles in the polar phase, the coupling to these clusters dominates. But for example, again, in this P1, when they are polar but not very persistent, what happens is that, again, as I said, there is this tendency to form these areas, so that some of them nucleate these zones of very strong inward order, but then this leads to an effective repulsion from the other. So collectively, again, if you look at the G of R in this region, what for two this was a clear repulsion, now there is an effective attraction. Because even if a few of them will repel, then in a way they expel the rest of the particles to be in a region where they are closer together effectively. So whether this will, I mean, how this will scale with size is something we need to understand, but this is just an indication that actually the concept of interaction and how you extract what would be the relevant many body interactions in a system of a suspension out of what you can learn from the behavior of a pair of these disks is still unclear, at least to us. It's not clear how to connect one to the other.
So one thing we can ask is, for example, are the interactions with this reciprocal?
Yeah.
So because you are not going to the fact that it's the difference between them.
Exactly. That's a very good, because we can measure the force on each of them, and indeed, then there is no reason why, and that's a good point. So I wanted now to go back to 2, and I said, I mean, here we are seeing how these disks really interact with the bath and how they depend on the morphology of the bath. But we wanted to look, I mean, at some point as we were trying to understand a bit more in detail fundamental nature of these interactions, we ask ourselves, what happens if you only have one inclusion instead of 2? It's like going back to understand. What I will show you, I changed now system because we had to reach large systems to really try to understand this interplay between an inclusion and the perturbation of the polar order. And actually there are, it is known that if you have porous media, or if you have a wall or a disordered wall, that has a very strong impact into how MIPS develops, for example. So we wanted to understand a bit more in detail what happens in the interplay between one of these disks and an active path. But in order to be able to reach large systems, we move from active Brownian particles to big check. Now we have point particles, standard big check with an alignment so that we can now have very large systems. We pay the price, or I mean, one characteristic of this system is that they are very compressible, more compressible than what I've shown you for the ABPs, even if they are compressible in the volume fractions that I was exploring, or area fractions. But here, then I have another phase diagram in the case of big check, where you modify the amplitude of the noise strength that you have here and the mean density. And then if density is low and noise strength is high, typically have a homogeneous disordered phase. And then as you decrease the noise, you will end up in the orientationally ordered liquid. And in between, there is the coexistent phase with bands. And we know that, I mean, this is goes back to the work of Big Check and Turner 2 to understand that you can break a continuous symmetry in 2D in these active systems. Now, what I will be looking at is what happens as we are typically in this region when I introduce a disk, okay? So the disk now is fixed. Now, for Big Check particles, when they collide with the disk, we have a collision rule that basically doesn't allow the particles of the bath to enter in the inclusion, and typically the orientation doesn't change. Or actually, we have a collision rule where we can change this angle, but I mean, if you want, we can discuss this later. But for the purpose of what I will be showing you, the angle doesn't change until noise will make them rotate. So this is a system. This is the inclusion. It's pretty tiny, and then this is this orientational order liquid. Again, color indicates the direction which particles are moving. Here you have all these black regions because of the high compressibility of the system, and then sort of like cold colors are moving to the right, and warm colors are moving to the left. So if there would be no inclusion, you would have this system moving along, and that's what you see. But then you will see that at some point around the particle, there is an event that triggers and generates a band moving in the opposite direction. And you can see how sort of like there are these events that are triggering, and then after some time, it will trigger a band in the opposite direction, and it will at some point reverse again. So this tiny particle is able to change the global order parameter of the whole system. It's not just a local fact. In fact, if we look a bit more in detail, so this is kind of like a zoom of one case that is better controlled. What happens qualitatively, we'll see now, is that as the particle is moving, you will see now the band moving from left to right. In the back of the particle here, if some particles turn out to be moving right, when they collide with the particle, they tend to stay there and keep on colliding with the particle. And it takes time until noise will allow them to move away. During that time, they can nucleate a bunch of particles that will be counter-propagating. And then as they escape, if they escape at a time that correlates with a low density of an incoming system, they can propagate and start collecting other particles. And apparently this is strong enough to be able to grow to the system side rather than being dissipated by the interaction of the counter-propagating bands at longer distances. Now you'll see that. So you'll see here the color. So this is one of the events where this happens, and we tracked it. And you can see how it grows. At some point, it just detaches. And then this detachment, I mean, that you saw here in the larger movie, in many cases, is destroyed. But statistically, from time to time, it works. And then it changes the global order parameter. Yes. Yeah. No, here there is, okay. So it's periodic boundary conditions. You mean, this is a crystal, yeah. Yes. Yeah. Yeah, the surprising thing to me is that this is a crystal at an extremely low volume fraction. So the point is that the deformation that it generates a counter-propagating band initially of the order of the particle, and this perturbation is able to grow to the system size. It's true that when you are sort of like half the system size, you can say, okay, now it's really filling the image. But this tells you that there is, the way I understand it qualitatively is that there are very long range correlations together with these high density fluctuations that are able to propagate a perturbation over very long distances. And eventually it's true, there will be the finite size. But I think this is intrinsic to the interaction of the disk with the perturbation and how it can propagate and relax at large distances from the perturbation source itself. What we try to do, yeah, I mean, we didn't look at scaling. What we did was, as you are asking this, we look at the global order parameter as a function of system size. And that's also, again, why we did this with big check, because then here we could have like 4 decades or 3 decades to see what's going on. And actually, this is the value of the global order parameter that you would expect for, I mean, in the absence of the inclusion. And actually, what this tells us is that there is I mean, it doesn't really relax, rather, it tends to decay when you go to large enough systems. So actually, we think of this as a chaotic system. You saw it in the first movie where you have these bands that, so there is first there is a probability to generate this counter-propagating band and can sort of grow. And then there is the relaxation time of the overall order parameter. And then at some point, system doesn't, I mean, if it would be only one of these bands, it would do that. I mean, there are cases where we saw it, I didn't show it here. When you see this counter-propagated band, it will then reverse, and then at some point it can relax to an ordered phase that will move in the opposite direction. And actually, when we look at the average phi, that side, that's what we're looking at. But at some point, these bands are being generated with enough probability so that then they distort the relaxation to this ordered phase. And it seems to get worse. I mean, at least over this, I mean, whether at larger distances it will come back or not, I mean, you can never say. But at least there is no clear, I mean, and this is all for the same phi. So actually here, the same, here, the system is less, from the point of view of the crystal, is less dense. No, the volume fraction here will be smaller than here.
Yes.
Yeah. This is actually, okay, I jumped to this because we were talking about this. I mean, we can look, sorry, and I come back. So we can look as we change the noise amplitude, what is the characteristic reversal, the time for these reversal bands. And I mean, this is the logarithmic. So I'm showing you this in the optimal case where we can gather more statistics. But of course, this will change. But again, I think that around here, it will be generic, change it, but again, qualitatively, yeah.
Third question. Position of the maximum depends on the size of the disk, and A over L is the only scale, or some other than scale?
I think there has to be another length scale, but I don't have an answer for that. But I think there has to be a length scale. Yes. It's not just the disk, because you saw that in a way the disk is able to generate counter-propagating bands. This size is related to whatever is the statistics for the bands, and somehow you should have a disk size that allows or favors. You will generate all sort of fluctuations, but you have to generate with certain probability those that correspond to characteristic band size or band correlations. Yeah. So I think it's there. If you change the disk size, these things shift around. We tried, I mean, again, for example, these two curves, which is the mean reversal time, corresponds to 2 size of the inclusion. So again, yeah, where you have the minimum changes, how frequent, I mean, how probable it is will also change, but the qualitative nature of this optimum that we understand, because here you have, you can generate many bands because you have the underlying band, and here as you move, when you decrease eta, you move deeper in the ordered phase. As you move deeper in the ordered phase, it's more and more difficult to destabilize them. Actually, we didn't see anything below 0.4, but I mean, whether it will stop here, I will show you We have some evidence that maybe there is a minimum eta below which then it's stable, but this curve itself doesn't seem to indicate that. So again, that's something that is.
So just this is the one with circles a smaller disk?
No, it's a larger disk. Yeah. But again, I find this a bit tricky in the sense that you can argue whether if we try to scale it as the ratio between the disk and the size, or if there is another length, whether we could collapse these curves or not. Yeah, that's still not clear, but yeah, it's an important question. So we looked at, I don't know. So we look at the, so in order to see how generic or how we can understand, we could gather better statistics. We also consider a case where we create initially, I mean, now there is no inclusion. We create a blob of particles, of big check particles that are moving in the opposite direction. And we vary the density and we see whether that will also generate this effect or not. And yes, it does. I mean, again, it depends on the density that we have and so on, but typically we can generate a band that counter-propagates. In this case, because it was only one blob, there is only this event. So here, the only thing we could look at is whether the probability for this counter-propagating blob really to grow to the system size. And by doing that, we could sort of like identify the probability, and we get something similar in terms of now, instead of the size of the disk, if you want, it will depend on the number of big check particles that we put in the blob. And also, we went to the kinetic models that we have or that exist to describe big check, because something this is like this. This is a way to recover Turner 2. If you write down an equation, a Boltzmann-like equation, assuming molecular chaos in the collisions at lower order, you can recover the hydrodynamic theory for flocking of Turner 2. And something we check is we try to see if with Turner 2 we could recover these counter-propagating bands, and we didn't. But so Turner 2 doesn't give an inversion. But then if you take this kinetic model, we went to then we like keep up to, for example, a certain K value, and then we truncate. So it's just quite a rough way to deal with the kinetic hierarchy that we have here. But then what we saw is for K larger than 5, yes, we could then observe counter-propagate. So this, and again, if we look at, in this case, when do we see that the solution of this kinetic model leads to a counter-propagating band? Again, it depends on eta. So as we decrease eta, now again, this is the ratio between the density of this counter-propagating initial blob. Below, say, 0.35, something, 4, we don't see it. So that's why I said that these results suggest that there may be a minimum eta below which then the system, the ordered phase, is robust enough against these perturbations. But I mean, this is the solution of the kinetic model. The numerics in the simulations, I mean, again, it's unclear whether this will become very unlikely or is really a fundamental reason why there is a lower bound for it.
So basically, when you say here, what you're saying is that you need to have high order gradient terms.
Yes, exactly. Yeah. So I think this is an example of why, or the importance, when I said, no, these strong correlations between order and density, they need to be captured. And that's not something you can recover with standard hydrodynamic description. Yeah, I mean, that's the question of merit. So this may give a hint, not to try to understand what are length scales that are relevant, or how the correlations, high correlations here, can be described as an effective additional term source. Okay, so and I wanted to finish by saying that, I mean, it's a PRL that appeared recently, I think it's in the last week, where they observed something similar. I mean, here I've talked about a continuous symmetry, which is this big check model. They analyzed an active Ising model, so this is now a 2D discrete symmetry, and they also observed something similar. So again, I mean, I've told you about this particular system, but maybe there is a more fundamental reason on how these long-range correlations and the nonlinearities in these systems really play a role in the destabilization of ordered phases. Okay, so I think the nature of an ordered phase, and what makes an ordered phase order and how it behaves, I think it's something that probably requires more thought. I mean, we have always thought, no, that Turner 2 was like the standard, but I think that there is life beyond Turner 2, and that's something that we should understand better. Okay, so in the last, can I take like, yes, still 5. So now in the last part, I wanted now to change gears. I've been going from interactions to disorder and chaotic behavior. I wanted to look now at another system where we have disordered, also now to show you or describe something different. I will be talking about the standard, I mean, again, the active pneumatics that I mentioned in the introduction is a model system where you have this, you know, these microtubules that are sort of like, I mean, together with the kinesin, they can be deposited typically experimentally on a two-dimensional substrate. And it is known that these exhibit an intrinsic, the isotropic state is intrinsically unstable. And this goes back to the work of Sriram Ramaswamy about the bending instability. And actually, I mean, we know quite a lot about this system, how it becomes unstable. And actually, what is interesting is that this type of chaotic flows are not something unique. I think this is a model system for this type of chaotic flows, but you can find similar or related type of chaotic behavior in many other active systems. So what I will be now looking at is about the nature of this chaotic flow in 2 dimensions and the nature of the defects in 3 dimensions. So for the 2D, we know that the active pneumatic is unstable. So there is a characteristic critical parameter that is the ratio between the system size and the active length. The active length in the active pneumatic is a ratio between the activity, the amount of energy that enters into the system, and the elastic energy cost to distort the pneumatic. I put the formula before the formula that I will show before, after, but so this tells you that if you go to the infinite system, it's always unstable for any finite system, then there will be a characteristic value of A. And again, you can understand that you will end up, I mean, there is a route to turbulence that is characterized by how this bending instability sets in. And actually, you have also time-dependent structures that are not chaotic, but change in time. So I think it's also something that we start understanding to try to classify this transition as we know for other dynamical systems. But I will not do that. I will focus directly once we are turbulent. So once we pass this threshold, and we know that there, if one look at the kinetic energy of the system, as a function of the wave vector, the spectrum is the way in which it's understood that is composed by at high Qs. There is a k to the minus 4 decay that was predicted by Guillaume, and which basically presumes that the system here is characterized by a number of vortices that are distributed exponentially in size. And then more recent work by Alert et al. Also say that if you have a Stokes equation, so this is strictly speaking zero Reynolds number, and because you have stresses at small scales, that can give rise to a q to the minus 1 spectrum. And actually, this is a theoretical prediction. These are experiments by Martinez-Pratt, where they, in a way, show that there is something that can be compatible to the k to the minus 4, then something compatible k to the minus 1, because you always have a liquid layer. At some point, the viscous fluid behind or above also matter. So asymptotically, there will be a coupling to the fluid phase. So that's kind of like the experimental evidence of this spectrum. Actually, whether this is really asymptotic or not is, I think, it's still not completely settled. So there is a work by Scutley where they do not study an active pneumatic, but they study active dipoles, a suspension of active dipoles. And their claim is that it's not k to the minus 4, and then at small q values, it tends to saturate. And what's the relationship between these two? I mean, for the active pneumatic and for a suspension of active dipoles, again, I think that's something that requires further thoughts. What I will be showing you is the numerical simulations that we have done with Lattice Boltzmann where we take the standard active pneumatic model. So we have, on the one hand, the Navier-Stokes equation, where the stress will have the standard viscous stress, the passive contribution. By this, I mean the elastic contributions, because we have a pneumatic liquid crystal, plus the active, which is, as usual, proportional to the degree of pneumatic order. And the passive comes from a free energy, that's the standard Landau, the Gens free energy, where we have is described in terms of the Q tensor. So we can quantify or control the transition between the isotropic and pneumatic, and then the elastic energy in the pneumatic phase is like the one constant assumption, so just this K that I showed before. And for the order parameter, the Q, then we have the usual expression with the molecular field here, and then the S, which is basically the coupling to the symmetric and anti-symmetric part of the gradient of the velocity. And then we have this parameter psi that tells whether the liquid crystal tends to align or tumble with the flow. And what I will show you now are results of how this 2D active pneumatic move by changing alpha. So in changing the sign, we will have contractile or extensile active pneumatics, and by changing this parameter theta, then we will have aligning on tumbling. And I repeat again, so this is a relevant active length scale. So the ratio between the elastic cost to the distorted pneumatic and the energy that we input. And the parameter A, I mean, we compute the parameter A using, in the parameter A, there is a length. So here, because we will have a time-dependent flows, we will identify a characteristic length from the spectra and also an active length for the spectra that we measure. So we can sort of like run simulations, compute the velocity, vorticity, Q0, extract the statistics for the elastic kinetic energy, and these are the typical spectra. So for contractile and extensile, so this is the elastic spectra. So typically there is a maximum at low Qs, at higher Qs that we use to identify this active length scale. And I mean, qualitatively, both decays, K to the 3, we could say that for contractile, there is a better well-defined length scale in which the elastic energy is brought into the system, is activated, and while for the extensile is much broader. When it comes to the kinetic energy, what you can see is that, I mean, these are the typical spectra that we have. And again, these are the Reynolds number that we measure. So we always work in parameters where at smaller scales, Reynolds number is small. But because we solve the Navier-Stokes equation, we'll have a flow, and then we can measure a characteristic Reynolds number based, for example, on the spectra that we have. And typically, well, I mean, so this is K to the minus 4. So we could say, well, it's kind of like K to the minus 4-ish, but there is always at sufficiently high Qs at departure. So again, whether K to the minus 4 is asymptotic or not is not clear to us, and that goes back to this reference that I mentioned earlier. And here at lower Qs, okay, again, if you can say the Reynolds number is not really 0, it's small, it's kind of like not too far, although it tends to saturate a bit at lower Qs. Yeah? Now we start exploring for example, the role of the flow alignment. And what you can see here now, as I said, the Reynolds number, initially nominal Reynolds number that you will put is small. Here's a picture of the magnitude, and so here's the magnitude of the velocity. And what you can see between contractile and extensile is that extensile tends to form structures. The flow domains, if you want, that form are more larger than in the contractile case. And here, again, these are quite busy figures, but actually contractile case at very small Reynolds number, this is the smallest one. I mean, there is a region that takes K to the minus 1, but it saturates. And then if at larger scales, at the end, the Reynolds number, as we go larger and larger, becomes non-zero, there is a deviation. The most striking case is the extensile, where we have, again, this K to the minus 4, which, again, is not asymptotic. But then at low Qs, then there is a K to the minus 5/3, which is essentially consistent. This is for flow aligning, is consistent with an inverse cascade. So basically what we see, so actually, and if we measure in this case is the kinetic energy, the total kinetic energy as a function of time, it's increasing in time. So this is a scenario where we have like the active turbulence that will coexist with an inertial turbulence inverse cascade in this two-dimensional case. And one visual way to look at this is if we look now at the vertical flow, vorticity, you will see that, I mean, this is generative in color is positive or negative vorticity. You have large fluctuations, but with time, this inverse cascade typically give rise to the appearance of two macroscopic vortices in the system. This is a 2D. Yes. It's 2D, inverse cascade. So you will see the two domains. So this is a finite size effect associated to this, the fact that the kinetic energy is growing in this.
And, how compressible is your?
It is compressible, but this is slightly compressible. Mach number is small. It's not zero again, but it's small. So again, we did then, I mean, how to sort of like try to identify the different scenarios. It's a bit demanding. So these are again busy figures where we try to collapse a lot of information. So we look at the effective A value. Now negative is contractile, positive is extensile, and then we can look at the effective elastic energy and kinetic energy that we have. And basically, we identified these three regimes. Blue are cases where the system is not turbulent. I said that you need like a minimum A to get turbulence, this chaotic state. Then green is what is the active turbulence. And then yellow is this when we observe this inverse cascade. And actually, then the color is, so that's the color. And then I mean, some symbols do not have the black rim, and others do. I mean, the thicker the rim is, the larger size. So basically, no rim is tumbling and rim is aligning, roughly speaking. So, and then what we see is that we observe this inverse cascade when we are extensile, we are aligning, and basically, if you look here at the elastic energy or the kinetic energy, okay, it increases or not depending on the values of the Reynolds numbers that we have. But the only correlation that we found is that clearly, while in the contractile case, there seemed to be more or less a strong correlation between the elastic and kinetic energy. Actually, the ratio doesn't change a lot. This suggests that basically, actually, this is consistent with the idea that here there is no transfer, no flow transfer between modes, and there is like a balance between the elastic energy and the corresponding kinetic energy at each mode in a Stokes type flow. That's not the case here in the extensile case, where there is a strong correlation in the sense that the kinetic energy proportionally increases. This is visually related to those larger domains that I was showing you in the flow field, even if it doesn't correspond to the fact that the elastic energy is being pumped also at this larger scale. So here really suggests that there is pumping of elastic energy at a given scale, and that is like being transferred to larger scales to lead to this inverse cascade. And this was 2D. Maybe I can, I mean, in 2 dimensions, we know that when we are in this state, we have these defects, which are plus 1/2 and minus 1/2, and these have been measured experimentally. In 3D, the measurement of these defects is more demanding, and we have developed a code to be able to track defects, to reduce defects to curves, to threads that then we can follow statistically. And this has allowed us to do a rather thorough analysis on the probability of the distribution of defect sizes. So this is the length of the defect. And again, you can have defects over, this is a very dynamic system. Defects are being formed, breaking, coalescing. Statistically, they are characterized by a broad distribution. And if we look at the morphological character of these defects, if the length of the defect is small, they really grow quadratically with the radius of gyration, and they become, say, they grow linearly at larger defects. And this corresponds, I mean, these are 2 examples. if the defects are small enough, they seem to be there is a kind of persistence, so they are more like a disk that moves, while when defects are large enough, they behave more like as a random walk. And accordingly, the small defects have a net velocity that will decay to zero for large ones. And the other interesting thing that we found about these defects, besides the fact that they are, so actually something else we did is this decay here is 5⁻², which is compatible with percolation. And the other thing that we found is that there is this tail here at very large defects. And we think this is a topological feature of the defects, because you can have defects that wrap on themselves, but then you can also have defects that through the boundaries will not be able to wrap. So this can be reduced to a point if you want, and this cannot. And those defects, if now we do the analysis of the two classes of defects separately, the number of wrapping defects, as we increase activity, we decrease this length, this number of defects will grow, and their typical size decreases. And while for these wrapping ones, they can break and become wrapping and non-wrapping. It's not that they are separated, but statistically, there is always a small fraction, actually an order 1 defect that is wrapping, that in a way coexist with the wrapping ones. And that is kind of related to this, to the appearance of this tail here at the end. But as I said, it's not that they are, this wrapping can break and then coalesce with another and become non-wrapping, but statistically, there is always a very large defect that spans the system and that coexists with the rest of the distribution. So I think I'll finish here, but I don't think I have to go. I think I simply will thank collaborators. Joan Codina, postdoc, and Jure, professor in Institute of Physics in China, were involved in the first part of the interaction. Hugh Chate and Benoit joined for the study of these counter-propagating bands and the destabilization of the Turner 2 and the ordered polar phase. And the last part about active nematics was done with Lino de Gregorio, postdoc in Barcelona, Cecilia, former postdoc when I was in SICAM, and Federico Toschi in Eindhoven. Thank you for your attention.
Thanks for a lovely talk. Questions?
It's a lovely talk, Ignacio. Can I just go back to the beginning when you were talking about the interactions between the particles in the active path?
Mm-hmm.
So in the passive picture, there's the osmotic pressure of the depletant in a reservoir in chemical equilibrium with the system. Counting at the risk of opening can of worms, do you know what the pressure is, and does it map in that way, the pressure of the active?
So we don't have here a bath, but we could measure the pressure. No, we have not measured the pressure. Could be interesting to measure that. But you know that also the measurement, the concept of the pressure is controversial. So I think it would, I think it's definitely interesting to measure it and try to do the analysis till the end to see how does that compare to the direct force measurement. Whether that's kind of the way to rationalize what we observe or not, that's a different, we haven't tried that. Yeah.
The first part, you mentioned that you have a collision rule with your obstacle, right?
Yeah.
In which the direction doesn't change, right?
Yeah.
Have you explored what happens if you relax this rule?
You mean in this case?
Yes.
No, we didn't. So typically here, we didn't. Why? Because at the end, we have it's like Brownian dynamics. So particles will come and naturally will move around. So if you want, in this case, there is no, I mean, we do not, the particles will not really enter simply because you have the potentials. So the continuity of the potentials will make the work. And we didn't think, we could have introduced a kind of like alignment or anti-alignment interaction as we did for the active particles themselves. We didn't do that. In the case of Big Shake, we had to deal with that separately because of the nature, because there is no potential there. And then there it was really like a bounce back, and then you can do a bounce back or you can do a reflecting interaction. There you have a parameter that then you can modulate to determine how much the propagation, the direction of in which they are moving correlates with the velocity itself.
because depending on the right, you can sort of tune the amount of out of equilibrium you are in the collisions. No, it can be dissipative. It could be an elastic collision. It can break the tail bar.
Yeah, my impression is that I couldn't think that the degree of the dissipation per se is relevant. It's more the correlation between the collision itself and how the particle is able to relax its orientation that matters. I don't know if it can be rewritten or restated in terms of this dissipation, but yeah.
Very nice talk. Have you explored how the reversal of this phase, how does it depend on the shape of it? The same number of things are reversed, but in different shapes.
So that's what we are doing now. So and I think there the main, I mean, it's preliminary, but I would say my way to think about it is that, for example, we are trying with an ellipsoid. So then there is another question about the torque and the alignment and so on, which is interesting in itself. But as you can imagine, the shape tends to align the polar phase along the longer axis, and also reduces the space that is left in this rear part to nucleate the counterpropagation. So it is there, but then it tends to be destabilized. There are pockets where it still persists, and again, because we have these two lengths and the role of these two mechanisms, the overall rationalization is not so easy. But yeah, that's clearly an interesting question. It's for people, yeah. It's not for us.
So in this obstacle part, so I think you mentioned that Tonner 2 doesn't give you this, and you have to go to higher gradient. Does the sign matter of those coefficients? I'm asking because can you cook up a fixed check like model, but like modify it strongly enough that you can get this?
You mean even at the hydrodynamic regime? No. We explore parameters. Again, I don't know. I would say no. Generically no.